So you hear about machine learning everywhere, right? But what does it actually mean for a machine to learn? It's not about memorizing a bunch of facts. It's about finding patterns. Today, we're going to pull back the curtain and walk through the entire life cycle of a machine learning model, from the very first piece of data to the final crucial prediction.
I mean, just think about your email inbox for a second. How does it just know which emails are junk? It's not magic, and it's definitely not some person writing a giant list of bad words. It's a machine learning model, one that's been shown millions and millions of examples to learn the subtle, telltale signs of spam. It learns and it adapts, and that is machine learning, working in your life every single day.
Okay, let's clear something up right away, because you hear people use AI and ML like they're the same thing. They're not. AI, or artificial intelligence, is the huge, grand vision, the big idea of machines that can mimic human intelligence. Machine learning, or ML, is one of the most powerful ways we have to achieve that vision. Think of it like this: a classic chess computer that just follows a bunch of pre-programmed rules. That's AI, sure, but it isn't learning. But your spam filter, which gets better and better at spotting new tricks without anyone reprogramming it, that is the power of ML.
So if we want to build one of these learning machines, where do we even start? Well, it might seem complicated, but it all boils down to 3 fundamental building blocks.
First, and honestly most importantly, you need data. This is the fuel for the entire engine. It can be just about anything: numbers, text, images. Think about customer purchase histories, weather data, pictures of cats, you name it. Without data, the machine has absolutely nothing to learn from. It's the essential raw material.
Okay, so if data is the ingredients, what's next? Well, you need a recipe. And that's exactly what an algorithm is. It's the set of step-by-step instructions that tells the computer how to sift through all that data and start finding those patterns.
And you guessed it. When you combine the ingredients, your data, with the recipe, your algorithm, what do you get? You get the final dish, the model. This is the finished product of the learning process. It's basically a big mathematical equation that represents the patterns the algorithm found. So when we talk about a model that predicts house prices, that formula is the model.
Now, to really work with data, we got to speak the language. So let's stick with that house price example. A feature is just an input, something we can measure, like the square footage of a house. The target is what we're trying to predict, in this case, the final sale price. An instance is just a single row in our spreadsheet, so one specific house with all its features. And the label, that's the known correct answer for that house, like its actual sale price of $500,000. Getting this vocabulary down is absolutely crucial.
All right, so we've got our building blocks, we know the lingo. But what are the different ways a machine can actually learn? Turns out there are really 3 main teaching styles we can use.
First up is supervised learning. This is like being a teacher with a perfect answer key. We give the model tons of labeled data. This is a cat, this is a dog, and its job is to learn how to predict those labels on its own. Then there's unsupervised learning. Here, we don't give it an answer key. We just hand it a giant pile of unlabeled data and say, find something interesting. It's great for discovering hidden patterns, like grouping customers into different types. And finally, you've got reinforcement learning. This is like teaching an AI to play a video game. It learns through pure trial and error, getting points for good moves and losing points for bad ones.
And get this, of those 3, supervised learning is king. It's not even close. It makes up roughly 70% of all the machine learning applications out there today. And why is that? Well, it's because having the right answers to learn from is just an incredibly powerful way to teach a machine.
Okay, now we're getting into the real heart of the matter, training a model. And let me tell you, it's not as simple as just hitting run. It's a delicate balancing act, and this is where the biggest challenges really live.
Now, here's maybe the most important rule in all of machine learning. You cannot use the same material for studying and for the final exam. It just doesn't work. So we always split our data. We have our training data. These are the practice problems the model gets to see over and over and over again to learn. And then we have the test data. This is the final exam. We lock it away in a vault, and the model never ever sees it until the very end. That's how we get an honest grade of how well it really learned.
And this really brings us to the fundamental goal of training. You see, all data, every single data set, has random quirks and errors in it. We call this noise. The whole game is to build a model that's smart enough to learn the true underlying patterns, the signal,
without getting confused and memorizing all that random noise.
And this leads to two classic mistakes. On one hand, you have underfitting. This is when your model is just too simple. It has what we call high bias, meaning it makes assumptions that are way too basic and it completely misses the real pattern. On the other hand, you have overfitting. This is the opposite problem. The model is too complex. It has high variance. It doesn't just learn the pattern, it basically memorizes the training data, noise and all. This is like that student who crams and gets 100% of the practice questions, but then completely bombs the final exam because they didn't learn the concepts, they just memorized the answers. This is what's known as the biased variance trade-off. It's a constant tug of war. If you make your model more complex to capture more detail, you risk overfitting. If you make it too simple to avoid that, you risk underfitting. The true art and science of machine learning is finding that perfect sweet spot right in the middle. So, how does a model even know if it's getting better? How does it keep score? It uses something called a cost function, or sometimes a loss function. This is just a score that measures how wrong its predictions are. The entire goal of training is to fiddle with the model's internal settings to get that error score as low as it can possibly go. So how does it actually do that? Well, one of the most popular methods is a really cool idea called gradient descent. Imagine you're a hiker lost in a super foggy valley, and your goal is to get to the lowest possible point. You can't see the bottom, but you can look down at your feet and see which way is the steepest way down. So you take a step in that direction. That's exactly what the model does. It calculates its error, it finds the steepest downhill direction to reduce that error, and it takes a tiny step. And then it does it again and again, thousands or millions of times, until it slowly but surely makes its way to the bottom of the valley, the point of minimum error.
All right, so our model has been trained. It's hiked down the valley, it's minimized its error, it thinks it's ready. So how do we know if all that work actually paid off? Well, it's time for the final grade.
This is where we do our evaluation. Remember that test data we locked away? Now's the time to bring it out. We feed this brand new unseen data into our model and see how it does. This is its final report card. This is what tells us how well it's actually going to perform out there in the real world.
Now, to get the best possible grade, we have a few more tools. We often use a validation set, which is like a series of practice exams to help us tune the model's hyperparameters. Think of hyperparameters as the knobs and dials you set before you start training. They're different from the parameters, which are the values the model learns on its own during training. And to get a really reliable score, we can use techniques like cross-validation, which is kind of like averaging the scores from several different final exams.
So after all of that, what's the one big thing to take away from this whole process? It's this: the goal is not memorization. Any simple computer program can memorize data. The true goal, the holy grail of machine learning, is generalization. It's the ability to take what it's learned and apply it accurately to new, totally unfamiliar situations.
So from figuring out what spam to predicting house prices, we've walked through how a machine really learns from data. It's this incredible cycle of training and testing and tuning, all in the service of finding the signal in the noise. Which really just leaves us with one big question to think about. Now that we have this incredibly powerful tool, what are the most important problems we should teach our machines to solve next?